Hi everyone, and welcome to this new tutorial for session 4. Today, I would like to continue what we did last week with numerical propagation. So we saw one way to propagate Hamiltonian, and today we're going to see some more details about this and how to make it faster. And then we will continue with INEPT, maybe do some phase cycling in the end. We'll see, it depends on how much time we take. So for numerical propagation, I would like to take an example, quite complex example, so that the process is slow to calculate, and so that we see the advantages of coding it better. So we are going to write everything we need to simulate the spectrum of ethanol, the proton spectrum. And today I'm going to use some functions that I've created to go a bit faster. So as last time, I did start by defining AI that I will use later on. And so ethanol has 2 equivalent protons on one side and 3 equivalent protons on the other side. So for example, to define the initial density matrix, I will use this function that I've created, thermal density operator, and explain to you in a minute how it works. So, I said that I'm 9.6 Tesla and at a temperature of 298 Kelvin. So this function, let's have a look at the help. It describes how it works. First argument, you give the nuclei that you want to look at. So I have 5 protons, and I describe them as 1. A carbon 13 would be a 13 in this vector. So for my 5 protons, I write 5 times 1, and then I give the field in Tesla and the temperature in Kelvin, and the options I'm not using now. So this generates a thermal density operator to start with, and without having to code all the Kronecker product and all this, it's a bit faster. So let's say that we work at 400 megahertz, because I've chosen the field corresponding to 400 megahertz. So I define a carrier frequency in radians per second. So I want to I will have 2 groups of protons A and B, and I will define them with respect to the carrier frequency. As last time, I'm gonna give them chemical shifts writing in this way. So for example, I don't take exact values from the literature. I just take some values, but I want to show the spectrum qualitatively, not with the actual data. So let's say that we have one that have 1 ppm, and the other group of proton has minus 1.5 ppm. Then this is the way I write the Larmor frequency. So I have my Larmor frequency that depend on the carrier frequency and on the chemical shift. I repeat what I said last time. Of course, it is not exactly the way you should write the Larmor frequency. You should have the reference frequency and the carrier frequency. But for simplicity here, I assume that it is the same. Mm-hmm. And then I have a J coupling in Hertz with some value. Now I need to create my angular momentum operators. For example, IZ. And for this, I have created a function that generates the angular momentum operator. So it's just named I. And again, let's look at the help. Let's here. So the 2 ways you can use it is to give a number of spins and the axis, which is what I did here. So I have 5 spins, and it's along the z-axis that I want to have the operator. But later on, I will also use this syntax with 5 spins. But if I only want to see, for example, I1z, I will write 5 and 1, as we will see. So I will need this operator, and the same for X and Y. So for example, if I run this code and just show this part, you see now it's a very big matrix, something that you don't want to code by hand all the time. That's why I've created this function. We will also need these operators. I have one Z, so almost the same. Oh, sorry, Z. And this time I write a 1. So this operator with a 1 here is only with it's the angular momentum operator for spin 1, but in the Hilbert space of 5 spins. So just to give a easier example so that it's clearer, this corresponds to spin 1 in a basis with 2 spins. Corresponds to this, and if I write 2, the second spin, so you see you have a half, minus a half, minus a half, in this case, a half, minus a half, minus a half. And this syntax is the sum of the two, and it is equivalent to this one as well. So this is just definitions of angular momentum operators, and I've made this function so that it's convenient to generate the operator that we often need. And I need it for the 5 spins. Oops. So now I have generated my angular momentum along Z for each individual operator and along the three dimensions for all spins together. With this, I can write my Hamiltonian. So first we have the Zeeman Hamiltonian, which is let's say that spin 1 and 2 add 2 equivalent spin, and spin 3, 4, and 5 add the methyl proton. Then here is, we write it like this. So this is the Zeeman part for spin 1 and 2. And then for the other ones. So please let me know if it is not clear. I assume that we understand what this means, but don't hesitate to interrupt me on this. Now I will write.
I think.
Yeah.
Sorry, I think there's a minus missing in DB. BE minus.
Here.
Up 2 lines.
Oh, thank you very much. That's very important. Yeah, you're right. Cheers. So now I write J between spins A and B. I will split it in 2. So this is for the interaction of spin 1 with spin 3, 4, and 5. So I will write it like this: 2 pi J. And this is the product of spin 1 and 3. I have to sum. Okay, let's make it a bit larger so we see better. So this is spin 1 interacting with 3, with 4, and 5. And here I don't write just for simplicity. I neglect the roof effect, so I don't write the X and Y terms. It's a truncated Hamiltonian. I do the same for spin 2. Spin 2 also interacts with 3, 4, and 5. So now I have all the interaction between the J interaction between the pair of equivalent protons and the triplet of equivalent protons. And H0 will be the sum of these 3 Hamiltonians. Okay, so now we want to pulse on these protons and see to generate our initial state in the transverse plane. I will write it slightly differently than last time. You will understand why probably later on. So I need my Hamiltonian for the pulse. Y. So I say I pulse along Y, and contrary to last time I was writing omega for the pulse, but to go a bit faster, maybe I should be clearer writing like this. So this is the Hamiltonian during the pulse, but already with a length. So when I calculate the propagator. Now I should write tau p, but I don't because it's already embedded here. So instead of writing omega I and then having time times omega I know that when I will multiplicate the time with the time of the pulse, I have the pulse angle, so it's a bit faster and clearer to write it like this. So this is a pulse along Y on all spins. So now what I did is I propagate this density matrix on this Hamiltonian, this propagator, but I don't create a new density matrix. I just erase the previous one because this is the one I will use all the time from now on. And from now on, we have to propagate. So I will create parameters as I did last time. I have 2 kilohertz of spectral window, and for n, I'm just going to copy it as I did previously. Don't explain this again. So let's go back. Let's go to our PowerPoint and see how we can propagate. So here you see the sandwich formula, and with the definition of the matrix exponential. And what I did last time is that I chopped the time into intervals that I've called here T1, T2, T3, and so on. And I've propagated. I've defined for each time interval. I've calculated the propagator and propagated from the starting point until time tk. This corresponds more or less to what I did last time, but I use a function called linspace. Then written in this way, if t1, so when k equals 1, t equals 0. So, written in this way, we have for k equals 0, you see for k equals 1, you see that time equals 0, and when k equals n, you get to the maximum of the FID, the time of acquisition. And so for row 1 will be the same as row initial. We haven't propagated anything. So this is what we did last time, but I have written this in a slightly more formal way, and we're going to start again this time with this method, and then see another one that will be slightly faster. So I define my time interval. I want numbers from 1 to n. So maybe you remember that this syntax, if I write this, for example, creates a vector. So I have numbers from 1 to n, and if I want to follow this syntax, my numbers from 1 to n, I have to put -1 and divide by n minus 1. So like this. So this is k now, and I divide it by -1 times the time of acquisition. So this is in fact exactly the same as what I wrote last time, which was this, which means a vector starting at 0, finishing at ac with endpoints. but I've just rewritten it in a way that is closer to what I've written here. So now I can do my for loop. I will call it K as in the PowerPoint. I need to create the vector of signal along time, which will be with zeros. So for each loop, I first have to calculate the propagator until this point. So I propagate H0, and this is during time Tk. Once this is done, I can calculate a new density matrix that depends on time. Ut using this matrix that I'm propagating. And then I need to extract the expectation values from this matrix. Again, I use what I've shown you last time. This is Ix. I force it to be real in case there are still some imaginary components. And to go slightly faster this time, instead of creating two vectors, I directly create a complex signal here. So I have only one vector where I acquire my signal as a complex signal. So I think this should be fine. I have defined everything. So I can now write the processing of this. So I ask the function to plot the spectrum. I have to add some line broadening, for example, 1 Hertz. So let's see what happens. I will probably have an error as often, but let's try. Oh, not too bad. I just forgot to remove the output, and I have to add a phase. So let's run it again. I just run this section. So you see the phase is in the wrong side because because of the way I've defined the pulse. So I can just add the phase here. So the phase is pi, and I also prefer to have it in ppm. So I give it the O1, and then I ask units ppm. Yeah. So what do we have? We have at 1 ppm a quadruplet, at a minus 1.5 ppm a triplet, which corresponds, as we can expect, to the spectrum of ethanol, where I have neglected the roof effect. Just to go back, this was indeed the value that we had chosen in the beginning, 1 ppm and minus 1.5 ppm. So this does work. It was not too complicated. Especially, I don't want to use too many functions because I want to show things from scratch, but I think from now on we can start using stuff like that to go a bit faster. But you really see in full all the operators. So this was one way to propagate the density matrix, and we can calculate how long it takes. In this case, it takes 4 seconds approximately. Now let's see the second method. Instead of looking at the time always from 0, I can consider the difference of time interval between all the points. And why does it make a difference? So this is delta t. This will be the time between each point. That is, you can calculate is the time of acquisition divided by n minus 1. And I calculate the propagator for this. Why is it faster? Simply because I calculate only one propagator. previously I had to calculate the propagator at each iterations of the for loop. This time I will calculate it once, and that will be it. I won't have to calculate it once more. Written in this way, the density matrix of of number k, when I start from k minus 1, so I take the previous density matrix, I propagate it to get the next one, using this propagator, which will be the same all the time. And this gives me the relation between k and k minus 1, and I just have to define the first one, which is rho ini. For example, for rho 2, you just apply once the propagator. For rho 3, you have applied it twice, and you see that this would be similar to starting from rho ini, but having 2 times the propagation. And this is correct, this formula here, to have the square that goes here. Really, this is a property of the propagator, because this is, you can prove it. It's not always true, but for the propagator, it is true. And if you write for rho k all this, you get to this formula, which is exactly the same that we had here. So I've written it slightly differently. I have written u of tk. Here I have written uk, but basically it is the same. It is a propagator at time tk. And you can prove it because tk is equal to this, so you can replace it. So what I wanted to show here is that I can propagate using the previous density matrix rather than starting from 0 all the time. And analytically, this gives me exactly the same results. So let's see in practice. This was propagation method 1. Propagation method 1. And now let's do method number 2. For this method, I have to first calculate. I will have rho k. No, let's start with calculating the propagator. So it's the same as here. I will call it delta t. So it's the propagator during time delta t. And delta t, we said it is ac divided by n minus 1. Because I will use it all the time, I calculate the inverse here. I don't know if it is much faster, but it doesn't cost much to do that. And now rho k is equal to rho ini. Remember that rho ini was defined here. It's the density matrix after the pulse. So now, if we go back here, we want to calculate for each rho k the expectation values and then propagate it again. So I'm going to write it like this. I first calculate this. Now I need to use rho k. And this I don't need anymore. Let's verify together. So finally I need rho k here. And let's try to think together what this is doing. So before I enter the loop, I define rho k as rho ini. So it means the density matrix just after the pulse. Now I enter the loop, k is equal to 1. So I'm going to fill my vector for the first value with the signal of rho k. And then I propagate rho k. There's a mistake here. Then I propagate rho k during time delta t. And I loop again. So this is not more complicated than this. The syntax is slightly different, but it will just be slightly faster. So let's have a look. I run it. And let's see if the signal is the same. Yeah. So apparently there's no mistake. And you see we have gain some time. I thought it would be much more interesting than this. It's approximately a factor of 2.5. But if you have a very complex system, I think it will start to be interesting. And so if we try to think why we have gained some time, here we will get in each of the iterations, we were calculating matrix exponential, and then we were doing 2 matrix multiplication. And again, some matrix multiplication to calculate the trace. And this time, we do the same multiplication for the trace, and only these 2 multiplication. We have removed the calculation, the computing of the matrix exponential in each step. And we really get to the same results. So this was the first thing I wanted to show today. It's quite technical, but I did this hoping that it can help understand really how you write the formally the numerical propagation. And I raise your attention to details like this. Even if n is very big, if you forget to put this one, you just say, oh, it's approximately the time interval is approximately the number, the time divided by the number of points. You don't get to the right results. And so now you see the peaks are no longer at the right spots. Why is that? It's because you have a slight imprecision in the time axis is badly defined. So at this very high frequencies, we are at 400 megahertz. It means that you are completely missing the frequency, and the result is that the frequency appears outside of the spectral window. And as we have seen last time, you have this refolding. So even if it's outside of the window, it appears somewhere on the window in a slightly random way. So you really have to be careful in the way you define your time intervals. That's why this method is slightly more straightforward to understand and encode than this one, but this one is faster. Okay, now I would like to talk about INEPT. So INEPT is I took this pole sequence because it's slightly more complicated than what we have been doing up to now, and it's an interesting process to illustrate product operator calculations. I'm not going to go through the analytical calculation, but I'm following more or less what you can find in P.J. Hall's book or Keeler's book in the way I write it. So in our case, I will be a proton, and S will be carbon-13. And we are going to show that this pole sequence allows to transfer the polarization from I to S. So we are going to code this in full. So let's start a new section. INEPT. Actually, what I had earlier. So now, let's say that our carrier frequency is 100 megahertz. We are still in a 9.6 Tesla magnet, but we are acquiring the carbon. That's why I define this frequency. And I will call my spins I and S to correspond to this scheme so that it's easier to understand. So I will be the proton, as I said, and its Larmor frequency is 4 times higher than the carbon, and then omega S will be this multiplied by some chemical shift that I have to define. Again, let's take any value just for the example. We add a J coupling between these 2 spins. And now what I haven't written here is that this delay tau has to be set to be exactly tau has to be 1 divided by 4 JIS. And we will see later on what happens if we move this delay. So this is the matching condition to have a perfect transfer in INEPT per sequence. Again, I will create my angular momentum operators. So for spin I have to write it like this. So I remind you, this means that these two means that I am in a two spin system, a Hilbert space of 2 spin half, and I want to have the angular momentum operator of spin 1 along x. For spin 2, which is labeled S, this is what I get. And now I copy this. I do the same for x and z, for y and z. Okay, so I have all my angular momentum operators that I will need later on. I write the Hamiltonian omega I IZ plus omega S times SZ. So this is the Zeeman term of the Hamiltonian, and now I write the J coupling path. Oops. And this time it's not too long, so I will not neglect anything. But then, if you're interested to see what happens if you neglect or not, you can just very easily modify this code. Yeah. Okay. So, but now I will define the propagator of h0, so u0 tau, during this this delay that I've defined here. I define it here because I will use it many times at least 2 times, and you will see that when we do the Refocused INPET, we'll use it even more. So what I miss now is my initial density matrix. And I will label the pulse sequence like this. So I start with row 0, and I go from 1 to 5, and 5 is the final one that I will propagate to get my FID. So this is like the labeling I'm going to use now. Row 0 is a thermal density operator. In this case, I have, for the first spin is a proton, and the second spin is carbon. This is the way I write it. I have this field and this temperature, the same as earlier. And from here, I can start to code the pulse sequence. So the first event in our pulse sequence, going from row 0 to row 1, consists in doing a pi/2 pulse along x on spin 1. So row 1, let's write it in full, this will be clearer. Row 1 is, sorry, h1 will be I1, Ix. So Ix is only acts on spin 1. And the pulse length, the pulse angle is pi/2. I can now calculate row 1 with this. So this is row 0. And now I can write it like this, AI. So I don't write it exactly the same way as I did earlier. I just don't want to define too many things that I will not reuse. So instead of defining U1, I write it in full like this. So this is a pulse along, let's write it like this, pi/2 pulse along x on spin I. What happens after this? After this, we have 3 evolution during tau. This means that row 2 is obtained like this way. So now I'm taking row 1 that I had calculated after the pulse here, and I propagate it with free evolution, meaning during tau that I have defined here. So this is the Hamiltonian in the absence of pulse, and this is the propagator of this Hamiltonian during delay tau. Free evolution during tau. Now, if we go back to the pulse sequence, to go to row 3, we have a pi pulse over x on both spins. Row 3 is, I have to define the pulse first. It's Ix plus Sx multiplied by pi. So to act on both spins, I have to sum the two angular momentum operators along x. I can repeat this. This is row 3, so I'm after the pulse. Now I have to propagate again during tau, which consists in just repeating this step to get the density matrix number 4, starting from number 3. And finally, the density matrix number 4 to go to number 5, we have to apply a pi over 2 pulse along on spin y, but this one on spin I, but this one is along y and along x on spin s. We copy this, is quite similar. So along y on spin I and along x on spin s. And this is a pi over 2 pulse. So let's have a look. We start with row 0 that was defined here. We propagate it with h1 defined here, which is a pi over 2 pulse along x on spin I. And we get row 1. Then row 1 is propagated with free evolution to get row 2. Row 2 has the effect of a pi pulse along x on both spins to get row 3. Row 3 has free evolution during tau to get row 4. And here we have, oh, no one told me that I did a mistake. This is along y, not along z. So I want to pulse on spin I along y. If you do notice a mistake like this, please warn me. Now what we have to do is to propagate this Hamiltonian. So I will use the same principle as here.
Okay, I was just wondering if it's more possible to write sort of in the middle of the screen, because when it's at the bottom of the screen, it can be a bit difficult to read if there's icons and things in the way.
Yeah, I try to think about it. Please remind me if I forget.
Yeah, it's difficult.
Yeah. I haven't defined my acquisition parameters, so I will do it here. Typically 5 seconds. Spectral window, I will make it a bit narrower than usually, so 500 kilohertz, 500 hertz. Let's write it simply. I want to see well, and I copy this formula here. So these are my acquisition parameters. Acquisition parameters. Now I define delta t as earlier. The propagation, the free evolution propagator during delta t is redefined now, and in its inverse. And now my initial density matrix is no longer rho ini. Rho ini was the name I used previously in this simulation. Now what I have to use is rho 5, which is, if you remember, it's the density matrix after the last pulse. This is now rho 5. I just need, I have to redefine this. I cannot do it yet. And I think that is all. Oh yeah, this is important. Now we have to define our receiver in a way. The propagation is correct, but here reading IX means that I'm acquiring the proton, while it's the carbon, the second spin that I want to acquire. So I have to replace by S here. And now let's plot the results. And I'm going to copy the parameters that I was using earlier. So I have a line broadening of 1 Hertz. I don't know if this phase is right. We will see in a second. I want to plot the spectrum. I tell it's the carrier frequency and the unit I want to process the signal in. Let's have a look. I forgot to define T. Okay, you see here this mistake. It's the same as here, so I'm going to copy it from here. I run it again. Okay. So this looks, this is not, the phase is not right. That's why we have these complicated signals. So let's change the phase. Not with pi over 2, for example. Check what it is. Yeah. With minus pi over 2. I don't know exactly which one, because that makes more sense. But so this is the antiphase signal that you expect more or less after an INEPT pulse sequence. And I think it is interesting to compare, because now we don't really see in this that we have transferred magnetization from proton to carbon. So to see this, this is a signal. I'm gonna rename it signal INEPT. And by the way, when you modify a variable like this, INEPT, you have the possibility to press on Maj and enter, and this modifies the name of all the variables. So I'm going to do the same as here, repeat it, but now for this one will be without transfer. What does it mean to do it without transfer? It will be the same propagation, but my initial density matrix will be as if I start with rho 0, and I pulse along. So I create a new Hamiltonian for the pulse with pi over 2 pulse along Sx. Yeah, Sx. So this is the Hamiltonian to pulse only on carbon spins with a pi over 2 pulse, and I will propagate it as earlier here. But it's starting with rho 0, and this is this Hamiltonian H pulse. So now what this code does is it starts with rho 0, which is the thermal equilibrium density operator for these 2 spins. Applies the pulse to get rho k and propagate it. So this is like a conventional ZG experiment. and this was defined earlier, so I don't need to copy it again. Okay. I do the same as here. I might have to change the phase. I run this code first. Now this is, oh, this is not running. Ah, it's just very fast. I thought it was bugging, but it's just very fast. Okay. So here you see the spectrum after the INEPT transfer, and here before the INEPT transfer. You see that the numbers, here it's 10 to the minus 8, and here it's 10 to the minus 7. So we do have a higher signal on this one. And for clarity, I'm going to plot them together. I remove this plot. I just need, so signal 1D can output the the transform signal, so I'm going to call it like this. What I just want to do is to show the two signals on the same plot. This is a mistake. This is not, yeah. In principle, yeah. So here I have a message here. Not happy because I should ask it to plot only the real part. This function signal 1D outputs a complex signal, so I have to plot. It's better to write real. And now let's zoom on this to see better. So we really have this was the signal before we did the INEPT, and you see that the signal is larger with the INEPT. So for example, if we wanted to show it to see something more impressive, we can replace it by nitrogen 15, for example. The frequencies will be completely wrong because it's 100 megahertz, but we don't really care in this case. Let's just have a look like this. I've run this part of the code and let's plot it. So you see in this case, because the magnetogeric ratio of nitrogen is even smaller than that of carbon. I think it's a ratio 10, more or less, with protons. This very weak peak is that of nitrogen without doing the INEPT, and the blue is with the INEPT. It's a good moment to take a break, and later we will see how we can do refocus INEPT and include a little bit of phase cycling in this.